Hello everyone, I'm Wonder Maker. Welcome to my channel. In the previous video, we completed the catapult launch of the small plane, but the power control part was not yet handled. In this episode, we will complete the power control module to achieve outdoor catapult launch. The entire module is divided into hardware and software parts. It achieves multiple functions such as portable mobility, remote control, adjustable catapult voltage, short circuit protection, and current and voltage detection. It can be taken out to play at any time. Let's talk about the overall design idea of the hardware part first. Use a 12V lithium battery for power supply. Through the boost module, the voltage is boosted to 48 volts. Then connect to two buck modules to reduce the voltage to 12V and 5V respectively. 12V is used to power the relay, which is the current switch for controlling the electromagnetic catapult. 5V powers the main control chip, remote control, and display. The connection state between the 48V power supply and the capacitor is controlled by a MOS tube. In the later stage, the capacitor voltage can be adjusted through the program to achieve catapult speed control. Since the energy stored in the large capacitor is large, the explosive power may be no less than a hand grenade. Therefore, a stainless steel pressure relief valve is installed to ensure upward release in case of an explosion. Safety first. The Arduino chip used in the previous issue was obviously not fast enough. So now I've switched to the ESP32 chip. The display is a 3.5-inch TFT screen, a very useful screen. Considering that mobile phones are often used for shooting in actual use, button operation is not very convenient. Therefore, I plan to use a wireless remote control for control. Several voltage dividing resistors are also integrated in the circuit board to monitor battery voltage, boost voltage, and capacitor voltage in real time. I repurchased a 200A current detection module. Although I feel that anything above 50A is actually a waste, it's not as effective as increasing the voltage. But it's better to be prepared. Finally, there is a power resistor, used to discharge the capacitor at the end. Assemble them all together. The hardware part is basically done. Then start the software code design.
2,000 years later.
After completion, it roughly looks like this. On the right are the charging port, the power discharge switch, and the power switch. Turn on the power, and the capacitor starts charging. The main interface displays battery power, boost module voltage, current, and set capacitor voltage. The set voltage can be adjusted as needed, and the adjustment range is 12-48V. These two values are mainly determined by the control voltage of the relay and 75% of the maximum voltage of the capacitor. Switching the interface allows you to view the speed measurement interface. In addition, there is a running voltage and current detection interface. Scrolling up and down provides more detailed power consumption data. Due to the large operating current, the relay remains normally open. The button has two modes, a single click for a 0.1 second energizing test mode. A long press for a 1 second energizing normal mode. The power and sensor interfaces have been uniformly replaced with commonly used XH2.54 and XT interfaces. Plug them all in and see the running effect. Verification passed. Now there is only one last step left, to print a 3D shell for it. Install a portable handle. After a lot of effort, it was finally installed, but I found that my handmade wireless antenna could not be used, so I had to buy another one. Adjust the voltage to the maximum value. Let's do a test run first. I didn't expect the scene to be so shocking at the time. It startled me, and I didn't even have time to shoot in landscape mode. Later, after careful investigation, the reason should be that the copper sheet was bent too high at that time, which caused a short circuit between the front and rear copper sheets. Start normal testing. Some people said in the last episode that the wind resistance was too high, so this time I used a train head to test the effect. It doesn't feel right. The speed didn't increase, but decreased instead. Test again without installing any accessories. The speed increased by 20%. I feel that weight is the key. Wind resistance is not important for the time being. The speed did not reach expectations, mainly for several reasons. First, the last measurement was not standard enough. Second, since the last time was a manual push, there was an initial speed. In order to prevent severe deceleration after adding a load, I finally prepared a slider with double the power. The matter of increasing speed, we will discuss it in the next episode. All preparations are complete. You can go out with the suitcase. Plug in the switch, turn on the power, and wait for the capacitor to boost the voltage. Let's try the big guy first, double the load. It looks pretty good, but the upward tilt is a bit serious. Try launching it again.
Oh God, please, no! No!
Forget it, trash plane, it's not worth it. The headwind is serious, let's change direction. Let's switch to Little Blue. Little Blue seems to have a crooked neck. Its tail was broken by my son a few days ago. Let's try the effect of the king of paper airplanes, Suzanne. It's okay, they fly as far as the slider flies, without any effort. I feel that the problem is not the catapult, but the poor aerodynamics of my little planes. Total annihilation, let's go home. The next episode will definitely be more exciting, remember to follow.